In late November, telescopes around the world picked up something no one expected. Spiraling jets of ice were erupting from a fast-moving object entering the solar system, a visitor now known as 3I/Atlas. The pattern of the plumes matched what scientists usually associate with cryovolcanic activity, the kind seen on frozen moons far beyond Earth. For the first time, a cryovolcano may have been observed on an interstellar body. Yet the strangeness did not end with the eruptions. The icy jets appeared in a consistent rhythm, and the object's brightness rose and fell in the same repeating cycle, almost like a heartbeat echoing through space. After each pulse, 3I/Atlas shifted slightly, changing its light curve and even its direction, as if responding to something unseen. Eruptions can be explained by natural processes, but a rhythmic signal paired with subtle course changes raises a different set of questions. If a cryovolcano can ignite in the darkness between stars, then what force is powerful enough to wake it? Long before the eruptions began, astronomers already knew 3I/Atlas was different. Its path through the solar system revealed that it did not originate here. It was cataloged as the third confirmed interstellar object ever detected, a traveler that had crossed light years before drifting into view. Most interstellar visitors pass quietly, leaving only thin trails of dust behind them. This one brought questions instead. As weeks passed, researchers tracking its motion began to assemble a list of anomalies, and the list kept growing. Within a few months, more than a dozen behaviors stood out. Each one difficult to explain on its own, and nearly impossible to reconcile together. The most obvious was the direction of its tail. Instead of streaming away from the sun like every familiar comet, 3I/Atlas displayed a structure bending toward it. An unexpected formation that challenged basic expectations of solar radiation and particle flow. Then came the acceleration. The object drifted faster than gravity alone could account for, yet it showed no clear signs of the uneven gas jets that usually push comets off course. It was not tumbling chaotically, nor shedding material in a way that matched the speed changes. The movement appeared controlled, but no known natural mechanism fit what was being observed, and still the anomalies continued. Its brightness pulsed in a repeating cycle, rising and fading with a rhythm that echoed through every dataset collected. The light curve formed a pattern so stable it resembled a time signal more than a random process. It behaved like a system operating on an internal schedule rather than a chunk of ice reacting to sunlight. Faced with so many conflicting clues, the scientific community reached for the one explanation that seemed to match the eruptions themselves. Cryovolcanism. Icy moons throughout the outer solar system have been seen releasing plumes of frozen vapor, driven by pressures beneath their surfaces. The spiraling jets observed around 3I/Atlas resembled those events closely enough to push the cryovolcano theory forward. It was simple, elegant, and for a brief moment, comforting. But it was also incomplete. A cryovolcano could explain the plumes. It could not explain the anti-tail. It could not explain the acceleration. And it had no answer for the heartbeat that kept flashing across the darkness. Which leaves one possibility that no one expected to confront. 3I/Atlas may not belong to any category of object that astronomy has ever named. It may represent a class of interstellar bodies that have existed for billions of years without ever being seen. And now, for reasons still unknown, one of them has awakened within reach of our telescopes. The first signs appeared as faint streaks on long exposure images, barely noticeable against the black of deep space. At first, observers assumed they were artifacts, the kind of visual noise that appears when a telescope pushes past its limits. But as the data accumulated, the streaks sharpened into structure. They twisted, they repeated, and soon, multiple observatories watching the object from different angles began reporting the same impossible shape, spiraling plumes of ice erupting from the surface of 3I/Atlas. These plumes were not random explosions. They unfolded in sweeping arcs that aligned perfectly with the object's rotation. Measurements showed that 3I/Atlas completes one full turn roughly every 16.16 hours, and with each rotation, the spirals recoiled outward like threads unwinding from a spinning core. The geometry was eerily familiar. Frozen moons such as Enceladus and Pluto create similar patterns when cryovolcanic vents release jets into space. Those spirals are shaped by steady rotation and pressure beneath an icy crust. Yet here was the same behavior, playing out not on a moon, but on an interstellar traveler that had crossed the void between stars. As attention focused on the plumes, spectral readings added another layer of strangeness. The object showed an abundance of carbon dioxide, far higher than what is commonly seen in comets within our solar system. CO2 is a known driver of cryovolcanic activity in extreme cold, capable of building pressure until frozen material erupts in towering vents. In that sense, the composition of 3I/Atlas fit the profile. The plumes, the shape, and the rotation all aligned with the physics of a cryovolcano operating in deep space. Yet the deeper the analysis went, the less the theory held together. Cryovolcanoes require energy. Internal heat, tidal forces, or radiogenic activity to force material upward. But there is no nearby planet pulling on 3I/Atlas. No clear source of tidal stress, no reason for internal heat to still exist after a journey lasting millions or even billions of years. In the outer ranges of the solar system, temperatures fall so low that motion itself becomes sluggish. Under those conditions, eruptions should fade, not flourish, and still, the plumes kept coming. The jets were powerful, structured, and persistent, defying every expectation for an object drifting through the coldest region of interplanetary space. That contradiction is what unsettles researchers the most. Something is feeding these eruptions. Something is sustaining them long after they should have gone silent. Which leads to the question no one has been able to answer. If the vacuum around 3I/Atlas is too cold to ignite activity, then where is the energy for these spiraling eruptions really coming from? As the spiraling plumes drew global attention, another detail hiding in the data began to reshape the entire picture. Most comets that drift through the inner solar system carry thick blankets of dust coating their surfaces. These layers are built over countless cycles of heating and freezing, forming an insulating crust that muffles activity beneath. But 3I/Atlas showed no such armor. Its surface appeared unusually exposed, almost polished by time, as if the dust that should have collected over eons had either never formed or had been stripped away long before it arrived. A bare surface changes everything. Without a heavy dust layer, vents and fissures can open freely across the entire body, allowing frozen material to erupt in ways that ordinary comets cannot. The plumes that traced spirals into space were not limited to isolated pockets. They seemed capable of emerging from almost any point on the object's surface, suggesting a level of uniform activity that defies traditional models of comet evolution. Then came the reflection data. When light bounced off 3I/Atlas, it did not behave like it does with typical comet dust. Instead, its signature echoed the characteristics of carbonaceous chondrites, primitive meteorites rich in dense metals. These materials formed during the earliest stages of cosmic history, before planets assembled into mature worlds. They are relics from an era when the galaxy was still young, and their presence on 3I/Atlas hints at a lineage stretching deep into time. Spectral analysis added one more layer to the mystery. Traces of nickel appeared in the readings, a metal often associated with primordial cores. It is found in the oldest fragments of planetary material, pieces that have remained unchanged since the first collisions shaped the early universe. If 3I/Atlas contains nickel in quantities strong enough to register across millions of miles, it suggests that this object may hold a core that predates most of the solar system itself. Taken together, these clues paint a portrait of something ancient and surprisingly intact. A surface scraped bare, a metallic signature rooted in cosmic infancy, and a body capable of erupting with the force of a cryovolcano despite unimaginable age. For an interstellar traveler believed to be nearly 8 billion years old, such activity should be impossible. The heat should have faded, pressure should have died, motion should have slowed to nothing. Yet 3I/Atlas is not quiet. It is not dormant. It is erupting with a strength that does not match its age. Which raises the question scientists hesitate to speak aloud. If time should have silenced this object long ago, then what exactly has awakened it now? As the plumes continued to rise from 3I/Atlas, another pattern began to emerge, one hidden not in its motion but in its light. Observers watching the object night after night noticed that its brightness did not drift randomly the way most cometary bodies do. Instead, it pulsed. The glow strengthened, then softened, then strengthened again, repeating with a consistency so precise that it stood apart from every natural fluctuation normally seen in icy objects drifting through space. At first, the pattern seemed like a coincidence. Comets often brighten when fragments break away or when sunlight strikes a vent at the right angle. But 3I/Atlas did not behave chaotically. Its increases in brightness are aligned with the timing of its eruptions. Whenever the plume surged upward, the light intensified, and as the jets weakened, the glow receded. The connection was immediate and unmistakable, linking its luminosity directly to its cryovolcanic activity. What made the phenomenon even more striking was how steady the rhythm became. The peaks rose at nearly equal intervals, as though driven by a mechanism operating from within the object itself. Each pulse appeared like a heartbeat reverberating through the darkness, flashing across the void with timing that would be difficult for even a machine to maintain under harsh interstellar conditions. The stability of the pattern drew attention fast, and independent analyses comparing data from different nights arrived at the same conclusion. The light curve was real, repeating, and unmistakably deliberate in its structure. Natural evaporation could not explain it. Sublimation, the process that drives most comet brightening, is influenced by heat, rotation, surface irregularities, and dust release. It fluctuates unpredictably, rising sharply and fading without warning. Nothing about it produces a consistent, clock-like pattern. And certainly nothing about sublimation causes an eruption to sync perfectly with a rise in brightness, cycle after cycle, with barely any drift in timing. For 3I/Atlas, however, the timing held. Every pulse echoed the last. Every surge matched the rotation. It was as though the object were responding to some internal pressure building, steadily and then releasing in a controlled burst, sending both light and ice spiraling into space. The predictability felt intentional, and the regularity was unsettling. If a heartbeat belongs to a system reacting to its environment, then what environment is influencing 3I/Atlas? What force, internal or external, could guide such a perfect rhythm across the emptiness of space? and if the object is operating on a schedule, the question becomes even stranger. What exactly is it responding to? As the heartbeat pattern deepened the mystery around 3I/Atlas, another feature rose to the surface, one so unusual that it challenged one of the oldest assumptions in comet physics. When the object moved across the inner regions of the solar system, the plume material drifting behind it did not trail away from the sun as expected. Instead, a distinct structure bent in the opposite direction, pointing toward the sun rather than away from it. This rare formation, known as an anti-tail, can appear under very specific conditions. Yet even in those cases, it never behaves with the clarity seen on 3I/Atlas. Anti-tails generally arise from particles aligned perfectly with the viewing angle, creating the illusion of a reverse-pointing tail. But the structure around 3I/Atlas did not behave like an illusion. It sharpened, widened, and shifted with the object's eruptions, suggesting that the material was being shaped by forces not typically present around interstellar bodies. The geometry puzzled analysts who expected the solar wind to dominate the direction of dust and ice. Instead, something was resisting that influence, bending the structure back toward the star it should have been fleeing. Yet the anti-tail was only the beginning. As the object continued its journey, its speed began to drift in a way that gravity alone could not explain. Most comets accelerate or decelerate predictably as they move around the sun. Their speed changes follow the shape of their orbit, and when deviations occur, they are usually tied to gas jets erupting unevenly from the surface. These jets can act like tiny thrusters, nudging a comet slightly off its gravitational path. But 3I/Atlas refused to follow that pattern. Its speed increased without a matching release of gas or debris, and the direction of the acceleration did not line up with any jets produced by its cryovolcanic activity. Instead of moving opposite to the strongest plume, the object shifted along a vector that seemed independent of its eruptions. The motion appeared guided, smooth, and consistent. Nothing like the chaotic tumbles produced by volatile gas on traditional comets. The more the trajectory was analyzed, the more the conclusion became unavoidable. If the acceleration did not match the known behavior of jets, then the acceleration was not coming from jets. Researchers found themselves staring at a path altered by a force they could not identify, a force that acted gently but repeatedly, bending the movement of an object that should have been drifting freely through sunlight and vacuum. And so the question hangs in the air, heavier now than before. If gas is not pushing 3I/Atlas, and if gravity alone cannot pull it along this path, then what is guiding its motion? What, or perhaps who, is steering it? For weeks, the motion of 3I/Atlas remained steady, predictable, and, despite its anomalies, mathematically traceable. Even with its strange pulses and unexplained acceleration, the object still followed a broad path shaped by its long interstellar journey. But everything changed the moment it swept through perihelion, the point in its orbit closest to the sun. That was when the object did something no one expected. It turned. Comets often shift slightly when heated, driven by uneven outgassing that nudges their trajectory. But 3I/Atlas did not drift. It pivoted. The adjustment was small enough to escape the casual eye, yet significant enough to alter the destination of an interstellar traveler moving at tens of thousands of miles per hour. And the direction it chose was the detail that froze analysts in their tracks. The new heading pointed almost directly into the gravitational domain of Jupiter, the region known as its hill sphere. This zone extends far beyond the planet itself and marks the area where Jupiter's gravity overwhelms the pull of the sun. Objects rarely enter it by chance. To do so, especially from an inbound solar grazing arc, requires a precise combination of timing, angle, and speed. The probability of an interstellar body naturally curving into such a narrow window is so small that some researchers described it as a coincidence approaching zero. Yet there 3I/Atlas was, carving a path that aligned with that improbable corridor. The shift sparked immediate questions. If cryovolcanic plumes had caused the turn, the direction should have aligned with the strongest jets. It did not. If uneven heating had been responsible, the curve should have reflected sunlight's influence. It did not. The change had no clear connection to the forces acting on its surface. Instead, it looked like a maneuver, a slight, deliberate correction, executed at the precise moment it would matter most. As projections were recalculated, the implications grew heavier. With the new trajectory, the object was no longer skimming past the outer planets. It was heading directly toward a region where Jupiter's gravity could draw it into a closer encounter. Alter its path dramatically, or even temporarily capture it. Such events are rare, unpredictable, and almost never triggered by small natural deviations. The deeper analysts looked, the more the adjustment resembled intent, not accident, which leaves one of the most unsettling questions surrounding 3I/Atlas. If that shift was not random, and if the odds of entering Jupiter's domain truly border on impossible, then what does that say about the path it is following? And more importantly, was this a coincidence or a rendezvous? As more observations poured in, the cryovolcano explanation, once considered the cleanest answer, began to fracture under the weight of the evidence. At first, it made sense. Spiraling plumes, exposed ice, and volatile materials erupting into space. But the deeper researchers looked, the more they realized that cryovolcanism could describe only a thin slice of 3I/Atlas. A surface-level behavior that failed to touch the larger mystery beneath. The first contradiction appeared in its acceleration. A cryovolcano can produce powerful jets, but those jets must push the object in ways that match their direction. 3I/Atlas, however, accelerated along a path that did not align with any visible plume. The thrust was subtle, persistent, and disconnected from the eruptions. No model of cryovolcanism could account for a force like that. Then came the strange layering of its tail. Instead of forming a single diffuse stream, 3I/Atlas produced multiple parallel structures, delicate sheets of dust and ice arranged with a precision that did not match the chaotic output of natural venting. Comets scatter particles in uneven bursts, cryovolcanoes release material in expanding cones. But this object created patterns, structured, sharp, and repeated. No one knew what mechanism could layer the tail so cleanly. The mystery deepened when analysts examined how the object polarized light. 3I/Atlas produced an unusually strong negative polarization, a signature far outside the range typically seen in icy bodies. Such extreme behavior suggested a surface texture or composition unlike anything cataloged in the solar system. Cryovolcanic activity could not explain it. The effect came from deeper physical properties, something woven into the object itself rather than into its eruptions. And then there was the heartbeat. The brightness rose and fell with eerie consistency, cycling with almost mechanical accuracy. Cryovolcanoes erupt in bursts, but their timing is irregular, shaped by pressure, heat, and unpredictable internal structure. Nothing about them generates a rhythm that keeps time across days and weeks. For 3I/Atlas, however, the pattern held fast. The cycle was not fading, it was strengthening. Piece by piece, the cryovolcano model fell apart. It captured the spectacle, but not the reason. It explained the plumes, but not the path. It illuminated the surface, but not the consciousness the rhythm seemed to imply. With no remaining framework that fit, some researchers quietly began to suggest an alternative. Perhaps 3I/Atlas does not belong to any known family of celestial objects. Perhaps it represents a category that predates our definitions, something older, stranger, and built on physics not yet understood, which leaves one final question lingering behind the data. If cryovolcanism is only the visible tip of the phenomenon, then how vast and how hidden is the part still out of sight? As the journey of 3I/Atlas unfolds, one truth becomes harder and harder to ignore. Everything about this interstellar traveler seems to sit on the edge of what science can comfortably explain. The plumes, the spiraling jets, the exposed surface, each detail supports the idea that a cryovolcano may be breaking through its crust. But surrounding that simple explanation is a ring of anomalies that refuse to fit. No natural model neatly accounts for the object's heartbeat-like rhythm, its non-gravitational acceleration, its layered tail, or its sudden shift toward Jupiter. Cryovolcanism describes only the beginning of the story. The rest remains wide open, and that is what makes this moment historic. Never before has humanity watched an interstellar body erupt in real time. Never before has a visitor from beyond the sun revealed behavior that seems both familiar and impossibly foreign. If 3I/Atlas is the first active cryovolcano ever observed between the stars, then we are witnessing a chapter of cosmic activity that no textbook has prepared us for. And if it is something else entirely, some older, stranger, and more intricate construction than nature usually allows, then this may be the first glimpse of a category of objects we have yet to name. The patterns it displays are not subtle, a rhythm that repeats with the steadiness of a metronome, a path that bends at the precise moment where the curve matters most. A body that lights and dims as if reacting to its own internal command. These signs could be innocent echoes of physics we do not yet understand. But they could also be something more, a form of signaling woven into motion and brightness, a language written not in words but in timing. This is where the real question begins. If 3I/Atlas is not only erupting but also broadcasting, intentionally or not, then what exactly is the message? Is the rhythm a natural consequence of pressure and rotation, or is it a pattern meant to be recognized? And if its trajectory truly aligns with impossible precision, what force sets it on that path? The universe has always spoken in light, gravity, and motion, but rarely does it speak in rhythms that feel deliberate. Rarely does it offer a mystery so complete that every answer leads only to more questions. So now the question turns to you. If 3I/Atlas is nothing more than a cryovolcano, then the mystery ends at the surface. But if it is something else, something not yet cataloged, then this may be the first signal of a frontier we have not begun to understand. What do you think? Is 3I/Atlas a natural cryovolcano, or is it the first hint of a phenomenon science has yet to name?